Howdy, and welcome to ASTR 402-602. My name is Dr. Rob Parks, and I'm going to be your instructor for this semester. I am very excited about teaching this course. I will be covering for Dr. Peter Plabchen, who normally covers this course, but is currently enjoying paternity leave. But I'm very eager to work with you all in terms of getting our hands on real data and doing a real science project, which is the main goal of this particular course. The way the course is going to be laid out is in an inverted format, meaning that I will be recording periodically videos like this one, where I will be giving you the bulk of the information that you will need to learn outside of the textbooks. You will watch these videos on your own time, as I said, outside of class. What I highly recommend doing is using the technique known as interweaving. So if you study topic A for 30, 45 minutes, you want to stop what you're doing at that time and then move on to topic B and study that for 30, 45 minutes. And then end there and move on to topic C or return back to topic A. Obviously, breaks in between are encouraged. Studies have shown that if a student participates in interweaving, their recall and their comprehension of what they're studying increases measurably. Probably because it's just simply more interesting. Our attention spans are fairly limited, and if you were to listen to me, as exciting as I am, for hours on end, you'd probably get a little bored after a while. So again, I highly recommend, if the lectures go longer than 30 minutes or 45 minutes, breaking them into smaller chunks and easily more digestible chunks. The in-class portion of the lectures, when we meet in class, will be split into two things. First, I will be talking about basically highlighting those key things or things I feel are most important in the lecture. So it'll be a kind of a mini little lecture. And also I will be, and then the rest of the time, you will be doing in-class activities, which would traditionally be known as the homework. You'll be doing that in class. If you don't complete them in class, then obviously they will become homework, but I'm giving you the opportunity to do that. Or, particularly as the semester goes on, that time can be used to complete work for the course, like work on your paper, work on your presentation, or work on the project data itself. And so it is very much of a active learning environment, or more of an active learning environment than you may be more traditionally used to. One of the resources I will be using is a Discord server. So if you have not already joined the Dr. Parks' Astroworld Discord server, please do so. If you need an updated link, let me know and I will provide you with one. What I'm going to be using the Discord for is primarily for announcements, but it also provides an opportunity for students to communicate with each other or communicate with me about questions in the class or just astronomy in general. So I'm hoping to be able to build something of a community within the class through the Discord server. I will be posting announcements, relevant announcements as we go forward, particularly in terms of whether or not the telescope is going to be, if the weather is going to cooperate and the telescope can be used on any particular given night. And I will also be hosting office hours virtually via Discord if you, for whatever reason, can't come to my office in person. So if you have any questions, please let me know, and I will be happy to answer them for you. The first class, the first in-person class, I will go over the syllabus. We'll get into some icebreaker kind of things, and then move on from there. All right, without further ado, I hope you enjoy this first lecture on coordinate systems. All right, so first lecture of the term. Let's get underway. Actually, let me turn that light off. It's a bit bright. So, what are we going to talk about today? What we're going to talk about are coordinate systems. So this isn't going to be, I don't anticipate this to be a very long lecture, for coordinate systems are fairly straightforward. Now, when you have to convert one from the other, that starts getting a little hairy. Start needing to do some linear algebra, but thankfully we have computers for all that nowadays. But let's start off simply and work from there. So before you can study something, the first thing you need to know about it is where is it, where it's located. And so that may seem obvious, but this has been a topic of study since the ancient Greeks. And so taking the first stellar catalog, the first catalog of all the stars by Hipparchus, we have expanded that work and mapped out the entire night sky. And hold on, I'm getting distracted by crickets. Much better. We expanded to the entire night sky, and we have determined, the International Astronomical Union has set down in stone that there are, in fact, 88 official constellations in the northern and southern hemispheres combined. Now, a constellation is, simply put, a collection of stars which have some form of significance to a certain culture. So, the vast majority of the constellations in the northern hemisphere are typically Greek in origin, although there is a robust Chinese constellation catalog, there is an Arabic constellation catalog, and so forth. But we typically have, in the West, held on to the Greek constellations of Cygnus, Lyra, Draco, and so forth and so on. In the South, it gets a little bit more weird. I don't really know who was doing the naming, but there are things like Pavo, which is a turkey, so things of that nature. So it gets, like I said, a little bit funky down there. In terms of astronomically speaking, what a constellation is you can think of it as a state. A constellation is a region of space where certain stars are located. So, for example, if I said that I was studying Lambda Andromeda, you would know that Lambda Andromeda is in the constellation of Andromeda, or the state of Andromeda, and you would then know essentially where in the night sky it would be located. You also know, roughly speaking, what time of year you would be, or I would be, observing said object, i.e. the summer, and so forth and so on. So constellations are not trivial things. They are very, very fundamental to our understanding of where things are located, and they have been quantified. If you look at the slide, you can see the light green lines are the borders. They almost look gerrymandered. I don't really know what political significance those borders were created, but those are the borders that have been created around the particular constellations that we know of, again, from Greek mythology. Now, how do we study, or how do we measure distances on a sky? So I'm going to be talking about later, basically, this concept of the celestial sphere. And so the principal idea is that the stars are very, very far away, to the point that we approximate, when we're just talking about looking at the night sky, we approximate it to be a 2D surface. And so when we look at the angles between, or the distances between two stars in the night sky, what we're really talking about is the angle between them. Now, we're going to be using the sexagesimal system developed by the Babylonians, where a full circle is 360 degrees, or a sphere encompasses 360 degrees. 1 degree can be split into 60 arc minutes, very much like 1 hour can be split into 60 minutes. 1 arc minute can be split into 60 arc seconds, and so forth and so on. A milli-arc second, for example, is 1 arc second split into million pieces. I don't know why it took me. That's a micro arc second. Sorry, 1,000 pieces. I don't know where my head is today. Anyway, to give you guys a kind of sense of scale of what these degrees look like, or what these measurements look like on the night sky, you could easily imagine 180 degrees is from west through the top of the sky to due east. So west to east going through the top, that's 180 degrees. Now, to get to smaller scales, the full moon is half a degree in extent for the most part. It changes based on where it is in its orbit, but on average it's half a degree in size. It subtends half a degree, or 30 arc minutes in size. And so 1 arc second would be equivalent to taking the full moon and slicing it into 30 even pieces. And the width of one of those pieces would be an arc second. So a arc second is a very small, at least visually, is a very, very small unit of measure. Other examples on here, if you find the Big Dipper, the 2 stars at the bottom of the bowl, those are approximately 5 degrees away from each other. If we want to use our hand, although that's a very, very kloogy way of doing it, an average finger is around 1 degree, would subtend 1 degree on the sky. The hook and horns hang 10 kind of symbol, that is around 20 degrees from tip of the pinky to tip of the thumb. But a fully outstretched hand is around 10 degrees. But again, to show you how kloogy it is, if a finger is 1 degree, then how is this 10? But that's, like I said, it's very, very approximate. So if you wanted to know how far up something is, typically you'll just fist over fist it in order to get up to the object of interest. Now, the most intuitive coordinate system that we use, and I am showing you the wrong screen. Oh well, we'll go with this. The most intuitive, I just realized that I'm actually recording the wrong screen. Anyway, welcome to how sausage is made in virtual learning. Anyway, the most intuitive version, the most intuitive coordinate system is the Altitude-Azimuth system. Now, in order to uniquely define the location on a 2D surface, you need 2 coordinates. If it's a flat plane, you need x and y to define a unique position on a 2D plane. If it is a sphere, then you need 2 angles. On the Earth, cities are uniquely identified by their longitude and latitude. Lines of longitude run north and south, lines of latitude run east and west. With this coordinate system, we have that the first one, altitude, is simply the height of the object of interest above the angle of height of the object of interest off the horizon, or a flat plane as defined by the individual observer's location. That's altitude. Azimuth is essentially how far around this flat plane do you have to turn in order to find the object of interest. And we define this, the 0 point, as due north. And azimuth is the angle from north through east. So north would be 0, east would be 90 degrees, south would be 180 degrees, west would be 270 degrees, and so forth and so on. So once you have the height above the horizon where an object is and where along the horizontal plane it is, then you can uniquely identify what that object is. Some points of interest in terms of the celestial coordinate system are zenith, which is directly overhead. The other point, which does have a name but is rarely ever talked about, is the nadir. That is the point directly beneath your feet. Obviously, from an astronomical point of view, you can probably understand why astronomers really don't care about the nadir. But I like useless trivia, so there you go. Zenith above your head, nadir below your feet. If you were to draw a line from from due north through zenith all the way back down to south, that would be known as your meridian or your local meridian. And the local meridian is useful because if you have an object on that meridian, when that object crosses your meridian, that is as high up as the star or object is going to get over the course of the night. So when you were planning out observations, when you were trying to figure out when is the best time to observe a particular object, you want to basically well, first off, you want to find out what time of year the object is up, but more specifically, you want to find the time of the day or thereabouts where the object is approaching the meridian well within the night. Like it's not crossing the meridian too early, it's not crossing the meridian too late. Essentially, you can get a full sweep. You can observe it for a long time as it goes across the meridian, or observe it when it's on the meridian in a very dark sky. So the meridian is the line, technically speaking, from north through zenith down to the south, and again, it is the point where a star is going to be as high up, or you're looking through the least amount of atmosphere that you will ever look at throughout the course of the night. So next, let's talk about the celestial sphere, and I mentioned this before. Now, the celestial, unlike what some folks might have you believe, humanity has known that the Earth is a sphere for quite a long time, pretty much since Aristophanes back in the yada yada BC. We've known that the Earth is a sphere. And so the early Greeks also imagined that the heavens were also a sphere. In fact, this idea of spheres was so indoctrinated by Aristotle that it took thousands of years before the idea that things could exist not in spheres or in perfect circles was actually entertained by the astronomical community. And so what the Greeks did was they invented this thing called the celestial sphere, and in practice what that is a sphere that is very, very far away, such that the distance to the sphere is far greater than the diameter of the Earth. And they essentially took the coordinate system of the Earth and mapped it out onto the celestial sphere. And so the celestial sphere has at least 3 points of interest right off the bat. You have the point directly over the north geographic pole, which we call the north celestial pole. You have the corresponding south celestial pole, which is over the south geographic pole. And then the equator expanded out to the celestial sphere is, imaginatively enough, called the celestial equator. Now, one of the issues with the Alt-Azimuth or Altitude-Azimuth or Alt-Az, as I'm going to continue to refer to it as, the Alt-Az system is that you have two problems with it. One, it's defined by your local observer. Therefore, if I say that a star is 45 degrees up and 13 degrees in azimuth, that is only valid for me where I am locally. If I tried to communicate that to someone in even just in the next state over, they wouldn't. It would be significantly far off. If I wanted to communicate that to someone, an observer who was, say, in Georgia, for example, they would not find the object where I was pointing it at. The other issue is because the Earth is rotating, Alt-Az coordinates are constantly changing. So not only when I say that something is, say, 40 degrees up and 13 degrees around, that is not only just limited to my own local environment, but it's also limited to that particular point in time. As the star rises, as time moves on and the star rises, its Alt-Az coordinates are constantly changing. And so the celestial sphere allows us the opportunity to define a coordinate system that fixes both of these problems. It allows us to create a coordinate system which is the same, the object has the same coordinates no matter where you are on the Earth, and also no matter when you are on the Earth. And when we look at the celestial sphere in terms of the local observer, what we notice is that the celestial sphere is tilted because of our location. If we are on the North Pole, then the North Celestial Pole would be directly overhead, and then all the stars would be what we call circumpolar. You would, if you ever had, I would love the opportunity to do this, either in the Arctic or probably in Antarctica. Freeze my balls off and look at the night sky, southern hemisphere, look directly up, and basically just watch the stars rotate around me. None of them are rising, none of them are setting. They're just rotating around in a circle. That has got to be mind-blowing, that experience. So if you're on the poles, everything is circumpolar, and circumpolar means never sets. If you're on the equator, nothing is circumpolar. If you're on the equator, Quinto, Ecuador, for example, folks there have the privilege of basically seeing every star on the celestial sphere over the course of the entire year. So all the stars rise due east, rise directly overhead, and set due west. Polaris is on the northern horizon, and the southern, basically the Southern Cross is on the southern horizon. And you see the sky rotate around you like a giant barrel or cement truck. Now, for the rest of us puny mortals who do not live in such particular locations, we see a mixture of the two. We see the celestial sphere as it's tilted. And so Polaris is going to be, Polaris, the North Star, which incidentally, the thing of note about Polaris, or the North Star, is that it's not that it's the brightest star in the night sky. That's a fairly common misconception. It's actually fairly dim. But it just so happens, and we'll talk more about that this later, it just so happens that it just coincides, its position just coincides nearly perfectly, not exactly, but nearly perfectly, to the North Celestial Pole. So if you take a time-lapse image like this one, what you would see is the North Celestial Polaris basically would stand still, as it were, and that the stars would make star trails, make circles around them. So in this case, what the photographer has done is opened their shutter for an extended period of time, and they basically have watched the sky rotate around that celestial pole. Your latitude is defined by the altitude that the North Celestial Pole makes from off the horizon. So Polaris is the only star in the night sky that has an altitude that never changes. Its altitude and azimuth never change. Its azimuth is roughly 0, and its altitude is equal to your latitude, your geographic latitude, as illustrated in these pictorial diagrams. And so not only do you have so when it comes to the coordinate systems, there are a couple of other lines of demarcation on the celestial sphere that you should be aware of. There is, well, actually, let me hold off and get to that in a moment. And when we talk about the equatorial coordinate system. Now, why do we really mention Alt-Az? I mentioned that Alt-Az has some problems, that essentially it's the Altitude-Azimuth Coordinate System has some problems. However, from an engineering standpoint, Alt-Az mounts are much easier to deal with. So if you see pictures of large telescopes, and what I mean by large is I'm talking the 8 meters, even the like the 5 meters in that comparable range, but definitely the 8-meter Gemini telescopes, the very large telescopes, the 10-meter Keck telescopes. These are all, and then future extremely large telescopes. I love how astronomers name things. These are all on Alt-Azimuth. It's just, well, when we talk about telescopes and optical designs, that will become more clear. And so they're just easier to deal with than equatorial mounting systems, particularly for something that huge. And like I said, because computers exist, it's pretty easy to convert from Alt-Az coordinates to equatorial coordinates and backwards and forwards. And so, if you were to, on the two angles that we use to define stellar positions or positions of any object on the celestial sphere, are right ascension and declination. Now, right ascension is equivalent to stellar longitude. Declination is equivalent to stellar latitude. Now, the 0 point of declination corresponds to the celestial equator. So the celestial equator has a declination of 0. If you're in the north, by definition or by convention, that is considered positive declination. In the south, that is considered negative declination. So if Polaris, for example, is plus 90 degrees. Let me think of something else. The lower half of Orion, for example, you're getting into like negative 5 degrees or negative 10 degrees declination for the lower half of the Orion constellation. So that's pretty easy to understand. Now, when it comes to the 0 point in right ascension, when we look at the 0 point of longitude, that was arbitrarily defined, well, not quite arbitrarily, it was the British. The British just said, you know what, we have the best navy in the world, we're exploring everywhere, we're going to define this how we want to, we're going to define 0 as going straight through our Royal Observatory in Greenwich, England. And that's that, because we've got a flag and we're going to plant it. So, the 0 longitude is the line of longitude which runs from the north geographic pole through Greenwich, England, down to the south celestial pole. Now, because things are constantly rotating, it doesn't quite really make sense to define the celestial or the 0 point in right ascension in a similar sort of way. So, even it's more of an arbitrary sort of way. We define the vernal equinox, or excuse me, we define the 0 point in right ascension as when the sun passes from the southern hemisphere to the northern hemisphere. And this is referred to as the vernal equinox. So, just taking a step back for a moment, one of the lines of demarcation that I mentioned before is, or that I mentioned that I was going to mention, is the ecliptic. The ecliptic is the apparent path that the sun travels over the celestial sphere. And so that is inclined by a certain amount, around 23.5 degrees, and if you can guess why that is, you deserve a cookie. Well, you deserve a cookie anyway. We all deserve cookies. If you can figure that out, great. If not, definitely look that up because it's important. So, it's inclined by 23.5 degrees. So the 0 point is defined as the sun is traveling along the ecliptic. It's the point at which the sun along the ecliptic bisect or traverses over the celestial equator. At that point, that is known as the vernal equinox, and that is the 0 point of right ascension. And so now we have a fixed coordinate system on the celestial sphere. The stars, to first order, do not move with relation to that celestial sphere. So to first order, we have a very good understanding of where things are, regardless of where you are on the Earth, and regardless of where you are, when you are on the Earth. So again, the angle from the celestial equator up is, or down, is declination. The angle from basically your meridian, either east is right, or east or west, is right ascension. Now, how does the sky look over the course of the night? how does the star's motion change over the course of the night? As I said before, if you're looking at alt-az coordinates, the altitude is going to continually increase until it gets to the meridian, and then it's going to decrease as it goes down. The azimuth, it's going to become more it's going to swing east towards the south, and then towards the west if it's in your southern sky, and the opposite if it's in your northern sky. It's going to swing northeast to northwest over the course of the night. For right ascension and declination, the right ascension and declination do not change for that particular star. That's because the entire coordinate system is rotating with the sphere. So a sphere does obviously travels 3. Let me try that. Take 2. A sphere rotates once upon its axis. It traverses 360 degrees. Now, that is approximately done in 24 hours, but not quite 24 hours. There is a difference between two timekeeping conventions, which I will talk about in next lecture, between what is known as a synoptic day and a sidereal day. Synoptic day is the time it takes to go from high noon all the way around back to high noon. A sidereal day is the time it takes to go from a star on the meridian to that exact same star passing on that meridian again, and that happens to be 23 hours and 56 minutes. I leave it to you, good students, to work out why that might be the case, and see if you're right when I post the next lecture. So the sidereal time is 23 hours and 56 minutes, more or less. That's the time it takes for the celestial sphere to rotate exactly once. What that means is that the sphere rotates about 15 degrees per hour. So if you want to, right ascension is measured in coordinates that are slightly odd. So altitude, azimuth, declination are all measured in degrees, minutes, and seconds. Or more properly, degrees, arc minutes, and arc seconds. Right ascension is a bit different. Right ascension is measured in hours, arc minutes, and arc seconds. And the reason for that is because the celestial sphere acts like a cosmic clock. And so if you know what the local sidereal time is, say it's 18 hours, it's currently, the local sidereal time is 18 hours. That means that the 18 hours of right ascension is passing along your local meridian. So the star Vega, for example, is passing by the local meridian. That is the time at which the star is going to be the highest overhead. If you have a star which is at 19 hours of right ascension, you know that it will take another hour for the star to travel up to the meridian and be on your local meridian. If, for example, moving back, 18 is back on the meridian. If a star has a right ascension of 17 hours, then you know that it has been that an hour previous it was on the local meridian and it is currently setting. That difference between the local the right ascension that is currently on the meridian and the coordinate, that is called the hour angle, and that again is rather important to know in terms of observing strategy. When you're trying to plan out your observations, it's very important to know what the hour angles are in terms of when the object is available. And the other issue is the lower in the night sky you look, the more atmosphere you're looking through, the more basically junk and the more distortion you're going to be looking through. So when the hour angle is large, that is not as optimal as when the hour angle is 0, because that means that it's on the local meridian. So declination is measured from minus 90 to 0 to plus 90. Right ascension is measured from 0 hours to 24 hours, or basically 0 again. So 0 all the way to 23 hours, 59 minutes, 59 seconds in RA, yada yada. And so, where was I going with this? I think I've covered everything on this particular slide. Again, the angles of arc are subdivided into 1 degree is subdivided into 60 minutes of arc. 1 arc minute is divided into 60 seconds of arc. If you want to convert right ascension into decimal degrees, what you would do is you would take the number of arc seconds, divide that by 60, add that to the number of minutes, take that number, divide that by 60, add that to the number of hours, and then divide that by 15, or multiply that by 15, and that gets you the coordinate system that converts from RA in hours, minutes, seconds to RA in decimal degrees. We'll talk more about that later on. The other thing that we need to keep in mind is that the Earth orbits the Sun at approximately 1 degree per day. And so when I said if you were sitting in Quinto, Ecuador, you could see potentially every star in the night on the celestial sphere if you wait long enough. Because of the Earth's orbit, only, as hopefully would be fairly obvious, you can only see the stars in the part of the celestial sphere that the Sun ain't. So the Sun is on one side of the Earth, you can see the stars on the celestial sphere, which is on the other side of the Earth. So at best, you can see half of the celestial sphere over the course of one night. That perspective slowly changes by 1 degree per day over the course of the entire year, in which case you can actually see all the stars. So, for example, the zodiacal constellations, which are the constellations that the Sun passes through at some point during the year. You're all familiar with the zodiac, the horoscopes, Aries, Pisces, yada yada. If you look at those constellations, those certain constellations are only available during certain months. So, for example, Virgo can only be seen from April to September in the northern hemisphere, whereas Aquarius can only be seen in January, February in the northern hemisphere, and so forth and so on. So, not only do we see different stars based on the fact that the Earth is rotating, but we also see different stars based on the fact that the Earth is revolving around the Sun. And so other points of interest are the vernal equinox, the summer solstice, the autumnal equinox, and the winter solstice. The equinoxes are when you have even days. You have the same amount of daylight as you have nighttime. Summer solstice is when the sun is high up in the nights or in the daytime sky as it's ever going to get, and you have around 14 hours of 14 and 10 daylight to nighttime hours. Winter solstice is the opposite. The sun is as low in as the daytime sky as it's ever going to get at noon. And you have 10 hours of daylight and 14 hours of darkness, again, depending on, mitigated by where you are on the Earth. The right ascension is listed here is the right ascension on the meridian at local midnight. So the vernal equinox has a right ascension of 12 hours on the meridian at local midnight. The way I like to look at this is actually 180 degrees off this. I like to look at what is the RA of the Sun at these particular times. So the vernal equinox, the Sun has an RA of 0 hours. Again, it's defined that way. The summer solstice has an RA. The Sun has an hour angle. Excuse me. The Sun has a right ascension of 6 hours. The autumnal equinox, the sun has an RA of 12 hours, and then the winter solstice, the sun has an RA of 18 hours. So, for example, if you're right now, if you're basically observing sometime in August, September, and you look at your target of interest, and it has a coordinates anywhere between, say, 10 to 14 hours in RA, forget about it. You ain't going to be able to see it because it's very close to where the sun is. So it's just a really quick and dirty way of looking at whether or not a particular target of interest is even remotely possible to be observed at any particular time. So just knowing where the sun is at any given point in the year, at least a rough handle of where the sun is at any given point in the year, can allow for very back of the envelope estimations of, okay, all right, I will be able, if it's in Cancer, I will be able to see that object during this time of the year, and so forth and so on. And so when we're talking about the sun's motion, when the sun is during the equinoxes, its declination is 0. At the summer solstice, its declination is 23.5 degrees. Like I said, the ecliptic is tilted. At the winter solstice, the declination of the sun is negative 23.5 degrees. So these are some questions that you can contemplate on your own. Highly recommend doing it. What is the right ascension? And I may even ask these questions in class. So I will be asking these questions in class, so definitely pay attention. Definitely look into this. What is the right ascension at the winter solstice? Actually, you can back it up, because I just told you. Can you find it on one of our celestial spheres? What is the maximum declination that the sun reaches? When does the sun reach that declination? And in Fairfax, what declination is directly overhead given those coordinates? So given what we've talked about, you should be able to figure out. So directly overhead is 90 degrees in altitude. As I stated before, you know that the North Celestial Pole, which has a declination of 90, has an altitude that is equal to your latitude. You should be able to figure out what the angle is given those measurements. The altitude equal to your latitude, and the fact that the object directly overhead has an altitude of 90 degrees. You can figure out what the declination is from there. Now, something you may have encountered is something called the analemma. Now, the analemma is a picture of the sun, and this is I believe it's a composite image. So it's basically the point. These were taken. 2 images were taken, one of the sun and one where the sun was blocked out, so you could actually see the surrounding environment. Because obviously, if you try to take a picture of the sun, it's going to blow. The light of the sun is going to wash out everything else in the image. So when you take a picture of the sun at exactly the same time every day, and you mark out where that position is, that is referred to as the solar analemma. And it looks like a weird figure 8. Now, again, I will leave it to you as an exercise to figure out why it is that in the northern hemisphere, the shape of the figure 8 is not symmetric. That the analemma is actually the upper loop is actually smaller than the loop at the bottom. And actually, next time I will start off the lecture by talking about why that is the case, revealing that is the case. So again, I will leave it to you as an exercise to figure it out over next time. And that is where I'm going to stop the lecture for today. Next time we are going to talk about time. We're going to be talking about different time coordinate systems in terms of time. Like I said, sidereal time, synodic time, and we're going to be talking about how those differences in time affect the coordinate systems that we have already talked about, the right ascension declination, and why things like precession need to be taken into account. Why the coordinates, even right ascension and declination, change over time. All right. I hope you enjoyed this. I certainly enjoyed giving this lecture, and I will see you all next time.